about vector addition. So in this section, we'll examine ways that vectors can be used in different physical situations by applying vectors to a variety of contexts. Okay, so with vector addition, we're going to learn two major ways of completing this. And this is like one is going to be by using a parallelogram, and then the other one is going to be the law, like the triangle law. Okay, so I'm going to give you an overview first, then we're going to go into specific questions. Okay, so to determine the sum of any two vectors, let's call them vector A and vector B, they have to be arranged tail to tail to complete the parallelogram form by the two vectors. So if you can see here, this is vector A and this is tail to the tail of vector B. And what we're going to do is we're going to take vector B and we have to rearrange it so it's head to tail. Okay, we're going to take this vector B and we're going to put it at the head of vector A. And their sum is the vector that's going to be diagonal in that parallelogram. Okay, and vector A, if you took vector A and put it in at vector B, you're going to get the same. This is going to be called the resultant. I usually put vector R for resultant. Okay, so our result, our sum is going to be this red vector right here. Okay, and the sum of the two vectors A and B is also found by translating the tail of vector B to the head of vector A. Okay, so this is essentially what we just did with this parallelogram, right? So just take vector B and put on the head of vector A, or even vice versa. And the resultant is the vector from the tail of A to the head of B. So from the start to the finish. So like this being the start, and then of course this being the finish, that's a resultant vector. Now, when we think about A minus B, so like the subtraction, what we can actually do is just arrange the vectors tail to tail, because what we actually have here is, like we have A and we have B, but essentially vector A minus vector B is just vector A plus the opposite vector B. Okay, so A minus, or vector A minus vector B is the vector that must be added to B to get A. This is the vector from the head of B to the head of A. This vector is obviously equivalent. We just said this. Okay, in other words, if we had vector A, which goes up like this, and B actually goes to the right. So if we had negative B, it would go to the left. Like we can say never eat shredded wheat, it would go to the west. Okay, and then this would be the exact same resultant. It would be from, if we looked at it as like addition, we would go from the tail of vector A to the head of vector B. And again, this vertical, it looks like it's going north. The vector is the resultant. Okay, now let's actually apply vectors. So when dealing with two forces that act on an object, so let's just draw an object here. Object, okay? We denote the first force as F1, okay, F1, vector F1, and the second force by vector F2. Okay, we use vectors in this case since the force that acts upon the object has both a direction and a magnitude. So the force could be, I don't know, 20, and the force here could be 30, for example. And then of course the direction of these arrows, or the direction of these vectors, I should say, is going to be the direction, of course, that the force is taking on. Okay, we use theta to denote the angle between the two forces. Note that this is the angle between the two tails. Okay, so angle between the two tails. So when they are sitting tail to tail, when you complete the parallelogram, it's going to be completely different. Okay, we'll have to use trig for that. We will use these in such examples as like two supports hanging from a ceiling. Say maybe something's hanging here from two supports, okay, and we have the forces going up. Or we could have a kid on a toboggan and his friends pulling him in two different ways, okay, or a car being pulled by like maybe even like a boat being pulled by two smaller boats. Draw one of those diagrams. Let's do it again. So here's the object. I'll just call it O this time. This is going to be F1 and we have F2. Okay, so when we have this diagram, this is what we're considering, okay? The direction of the force exerted by each of these forces, like each of these vectors, is indicated by the direction of the arrows. Okay, the magnitude of the force exerted by each of the two forces is proportional to the length of the corresponding force vector. So basically, if you measure this or if they give you a measurement, that's the magnitude of it. Okay, we're assuming that. Okay, and the force, let's say forces that have been exerted have been applied at a common point. Okay, that means that this angle here, theta, which we already know, we call it theta, those two tails meet at a common point. Okay, the resultant will be the direction of the object and the force at which it is moving. Okay, so maybe it's going to be a dad and a kid pulling somebody on a sled. The dad's going to pull with more force because he's stronger. Therefore, it's going to go more in toward the direction of the father, just as an example. Okay, to find the single vector, we combine F1 and F2 by drawing that parallelogram. Okay, so we can draw F2 here. Okay, and we can draw F1 here. And where they meet, so this green right here, this is going to be actually the direction and the magnitude that both of the forces are equaling. Okay, so the main diagonal of that parallelogram, again, this is called the resultant, so we can call it vector R, or the sum of the two vectors. Okay, and it represents the combined effect of the two vectors. Okay, we talked about this and I explained it, but here's formally the parallelogram for adding two vectors. Okay, to determine the sum of two vectors, vector A and vector B, so vector A and vector B, complete the parallelogram formed by these two vectors when placed tail to tail. Okay, their sum is vector AD. So, okay, that's D, the diagonal of the constructed parallelogram. Okay, that's A plus vector A plus vector B. Okay, I want to point something out here. This angle, tail to tail, is theta. We know that. If you guys remember the C pattern from like grade 9, okay, these two angles add up to 180 degrees. That means that this angle here is 180 minus theta. So example 1, given vectors A and B, such that the angle between the two vectors is 60 degrees, vector A, the magnitude of vector A is 3, and the magnitude of vector B is 2, determine the magnitude of A plus B. Okay, so this is 60. Okay, if we have that and we have to add the two vectors, let's do the parallelogram. No big deal. This angle in here is going to be that 180 minus 60. Okay, it's going to be 120. So now, like sometimes this gets a little bit sloppy, but what I do is I just take this over here. We know that this is 120, this is 3, and this is 2. Well, what law do we have to use now? We have to use cosine law because we want the magnitude of this side right here. This is A plus B. Okay, so we have to use cosine law. So just to review, let's call this A squared equals B squared plus C squared minus 2BC cos A. So A squared equals 3 squared plus 2 squared minus 2, 3, 2 cos 120. Okay, if we plug that into our calculators. So 9 plus 4 minus 2 times 3 times 2 cos 120. I get 19, so root 19. Okay, so the magnitude of A plus B equals root 19. Necessary to draw the parallelogram each time. I personally like it because then I can see the angles, but you can also use the triangle law of addition. Okay, so in the diagram here, B and A are not drawn tail to tail. See how there's like a huge gap here? So what they just basically do is like they draw A first, right? Vector A first, and then what they do is they attach vector B head to tail. Okay, remember the resultant is always head to tail. Okay, and then they get the resultant. Okay, and then it just says here in either way the sum is AC. You can do vector A first, or sorry, vector B first, and then A, and the resultant is going to be the exact same thing. Okay, now the zero vector. When two opposite vectors are added, the resultant is the zero vector. Okay, so in other words, let's say vector A plus negative vector A, that's going to be the zero vector. The zero vector has a magnitude of 0, and because it's a magnitude of 0, there's no actual direction. Okay, it's not going anywhere. So the magnitude, again, these are magnitude of vector 0 equals 0. Okay, let's try example 2. Suppose you're given the vectors A, B, and C as shown below. Using these three vectors, sketch A minus B plus C. Okay, so I'm actually going to start right on A. So this is going to be A. Perfect. Okay, minus B is drawing B, but in the opposite direction. So instead of going, let's call it, again, never eat shredded wheat, let's call it east. Instead of going east, what we're going to do is we're going to draw B, but going west. Okay, so that's negative vector B. Okay, and then plus C. So C goes up. So we left off at the head of B, or negative B. Let's go up C. Okay, and then this is vector C. Therefore, our resultant, I'll do it in like a deep purple. Our resultant, so this is the start, this is the finish, this is going to be the resultant. Okay, and that's it. Okay, we touched on this, so we're going to go over it formally now. The difference of two vectors, so like A minus B. In the diagram below, the difference between vectors A and B is found by adding the opposite vector B to vector A using the triangle law of addition. So we talked about this. Vector A is going to stay the same, but instead of vector B going to the east, B is now going to the west. Okay, and we saw that on the last example. So A plus negative B is also just called like vector A minus vector B. Okay, example 3. In the rectangular box shown below, OA equals vector A, and OC equals vector B, and OD equals vector C. Okay, so what we're going to do is we're going to express each of the following vectors in terms of A, B, and C. So basically what we're going to do is we're going to add and subtract. Okay, so we're going to add and subtract A, B, and C. So how do we get from B to C? Okay, so from B to C, I would say it's just the opposite of vector OA. Okay, so OA goes here. The opposite would be negative OA, which would be AO. Okay, same thing. GF. So let's go G to F. Sorry, I want to revisit that. Let's call that negative vector A. My mistake. Okay, GF is just the same as vector A. That's an easy one. Okay, let's switch up the color. OB. So from O to B. How are we going to do this? So we can go OA, which is just vector A, and then we can add OC, which is the equivalent to AB, so vector B. So OB is equivalent to vector A plus vector B. Okay, AC. So A to C, we can go negative A, negative vector A, and then plus vector B. Okay, BG. So starting at B and going to G. So let's go B to F. So let's go up first, which is equivalent to vector C. And then let's go over, which is equivalent to negative A. So negative vector A. Okay, and then OF, so starting here and going in behind to F. So let's go OA, which is vector A. And from here to here, let's go back to AB, which is vector B. And then let's go up, which is vector C. So vector A plus vector B plus vector C. Okay, now when we talk about bearing, we talk about the direction of an object and is measured in degrees from due north. Okay, so for an example, such as 160 degrees, if we talk about the bearing, we talk about north and then we go 160 degrees, which is about here. So never eat. Okay, so this angle would be 160 and then this angle in here would obviously, it'd have to be 20 to work our way to 180. Okay, so when we talk about bearing, it's just, you just get an angle and that's it, but you have to know it goes from north and then it travels clockwise. Okay, when calculating the velocity of an object such as an airplane, the velocity must always be calculated relative to some fixed object. Okay, there has to be some frame of reference. For an example, an airplane can be traveling, but it could be relative to the ground if you want to just compare it to how fast it's going toward the ground, or if you're driving in a car, it could be relative to how fast you're going in the car, or relative to like wind speed. Okay, it just has to be relative to something. So when we measure velocity relative to the ground, it's referred to as ground velocity. Okay, so example 4, an airplane heads due south at a speed of 300 kilometers an hour. Okay, so south is down, and the magnitude here of this vector is 300 kilometers an hour. It's kilometers. Okay, and meets a wind from the west at 100 kilometers an hour. So when we talk about from the west, it's coming from west and it's going east. Okay, so it meets a wind from the west going 100 kilometers an hour. This to me is really easy to do with triangle rule because we went from north to south. So tail to head and then tail to head again. Okay, what is the resultant velocity of the airplane relative to the ground? Okay, so we know that we're just going nicely west and we're going nicely south. So these angles are going to be 45s. This is going to be a right angle triangle. So we can actually just use Pythagorean's theorem. Okay, so let's talk about the magnitude of r equals 300 squared plus 100 squared, all rooted. So the magnitude of r equals, so 300 squared plus 100 squared, root that. Let's round it to 316.23. Okay, kilometers an hour. So that's how fast it's moving. Now, because it asks us specifically for velocity, we need a magnitude and a direction. So now let's actually solve for the direction. I'm sorry, these are not 45s. And it can't be 45s because this is 300 and 100. I was thinking 45 just simply because it was west and east, but it's going to cut more on an angle. But we still have to figure out this angle here. So we can go, we can use tan theta equals 100 over 300. Okay, so theta equals tan inverse of 1 over 3. And I get 18.4 degrees. So this angle right here is 18.4 degrees. So the airplane is flying at 316.23 kilometers an hour at an angle of south 18.4 degrees east. Okay, so when we read this, we read starting south and then move 18.4 degrees toward the east, which is here. Okay, the other way we can do it is with that bearing. Okay, so because it's 18.4 here, we can do that 180 minus 18.4, and we get 161.6. So we can also express our answer as the plane is moving 316 kilometers per hour at 161.6 degrees.